Just a heads up, this is going to be a pretty long video. The equations I show will be the basic calc and trig, but there were a lot of little complications that kept popping up that I had to sort through. And I would rather have a long video that's like a comprehensive text that I can look back on later, or anybody can look back on later, to sort through all these tiny details. Because if I just post a really short video on the answers and how to get them, it just leaves many questions unanswered. I was curious about the efficiency of a paddle wheel, because if you have a paddle wheel right here, this would be kind of like the worst case scenario where the water level is at axle level. As the paddles come down, they're going to smack the water and push down on the water instead of pushing it backwards in the X direction. This paddle wheel scenario where the water is at axle level, that's not realistic. I just wanted to do the math on it for a learning exercise. So if you take your paddle wheel and you raise it up so that the paddles contact the water at 45 degrees, then you're going to have more of your force pushing in the X direction backwards instead of pushing down in the Y direction. I figure this problem would be interesting to someone that just had their first calculus and their first trigonometry class, and they want to know how they can apply that information and those problems and those graphs, because as far as I can tell, I think this is probably about as simple as it gets for coming up with a word problem for calculus and trig, because it's just all, like your first semester stuff. So there's nothing advanced here. There's no advanced equations or anything more advanced than just the basic calc and trig that you would use, or that you would learn in your first classes. All right, so what I said right here, basically what this is, I think, is just the average sine value of the paddle as it comes down. So one way you could do this, for example, right here where the paddle strikes the water at 0 degrees, you could just take the sine of 0 degrees, because the sine of 0 degrees will be 0. So that means you have no force pushing, you have no force pushing in the X direction. All your force is in the Y direction and being wasted. Then you could take the sine of 1 degree plus the sine of 2 degrees, sine of 3 degrees, all the way up to sine of 90 degrees. There will be 91 numbers there total, because we did sine of 0 to sine of 90. So you could just add up all your sines, divide by 91, or you could do every 5 degrees or every 10 degrees to get a ballpark value for an average sine value, and that would tell you the efficiency of the paddle wheel. And in this case here, where we raise the paddle wheel up to where the paddles contact the water at pi over 4 or 45 degrees, then you would just you could just take sine of 45 plus sine of 50 plus sine of 55 or whatever, and then get an average sine value between 45 degrees and 90 degrees. Notice also I flipped my unit circle upside down just for the ease of math. All right, so I got the answer on this the first way easily by just doing an average sine value, but I'm going to show how to get the most precise answer using the area under the curve. And I'm actually going to use two methods of the area under the curve to get that answer. So I got the answer and I was okay with that. I posted this video, but the problem was I really didn't know what the answer represented. Was it the efficiency, or was it also the energy? Because force times distance equals your energy, and we have a force that we're pushing down and pushing that water a certain distance, or pushing the paddle wheel boat a certain distance. So I couldn't really tell if I was getting efficiency or energy or both from the graph. So I got my final answer, but I basically didn't really know what that answer was for sure. So that's what took me so long to figure this out, and I got a few pages to explain that. So first off, the graphs that I'm going to show, they're going to be for efficiency, not the total energy. And to get a better handle on that, we could look at, say, a tracked amphibious vehicle, where some of these amphibious vehicles have these tracks, and these tracks act like paddles to push the vehicle through the water. If you want to get the energy that one of those paddles pushes, you could just make 1 your value for everything. You have a distance from here to here the paddle will push. The mass of water could be 1. So you have a distance of 1, a mass of 1, acceleration of 1. Mass times acceleration is force, therefore your force would be 1. Force times distance is energy. If everything equals 1, then your energy is 1 for that volume of water or mass of water that you push. So this is just one example here of thinking about the energy of the water being pushed. What I said here is this is 100% efficient because these paddles are just pushing in the X direction. Say we have a very long track, so we're going to ignore these little tracks coming down here at the angles. Right when these paddles or these treads hit the water, they're going to push down on the water instead of pushing it back. But most of the travel of these tracks will be in the X direction. So I'm going to consider this basically a 100% efficient situation. And if you want to look at the actual energy that's involved here, like I said, if you make everything one, mass, acceleration, force, distance, it's all one, then you could have your XY graph right here. Here's your paddle right here, or your track, or the tread or whatever on the track. It goes down one, it'll push the unit of water back one, so you have 1 times 1 is your area. That could also be your volume if you make the depth one also. But anyways, your area is going to equal the amount of energy in the X direction. So it'll just be 1 times 1, which will equal 1. So this is one way to think about the amount of mass that you're pushing, or the amount of energy you're pushing in the X direction. I'm going to show another paddle wheel example though, and I'm not going to really look at this anymore because everything else I'm dealing with is going to be in a circle form or a wheel, and not a track form or a linear form. I'm just showing this track form right here just to get a better or a deeper understanding of what it is we're looking at and how we're pushing water, and the different ways you can push a mass of water backwards to get your energy. For a 100% efficient paddle wheel, I'm looking at a vertical bucket paddle wheel right here, which is also called a 4-bar linkage system or a 4-bar mechanism, because you can have a bar right here on the left, one on the right, and then these 2 horizontal beams or horizontal bars. The paddle wheel will be the vertical component right here, and you could have a motor either at this pivot point or at that pivot point. As these horizontal bars swing down here, then this vertical bar will remain vertical. And maybe you can imagine as these horizontal beams swing down to say 45 degrees right here, they have to maintain the same distance with this vertical beam right here, so that's why it'll stay vertical. And you can actually make a really simple model of this with just something like construction paper and paper clips ran through for the joints or something. So anyways, this is a 100% efficient system, and I'm not considering the efficiency of the motor or the friction of the gears or the parts or anything like that. I'm just talking about efficiency, meaning that we're just pushing the water only in the X direction and not in the Y direction. The area or the volume of the water that we're pushing, area and volume, can actually have the same number. If you just make your volume 1, that'll be proportional to the mass of the water that we're pushing, which is also proportional to the force, which means it's also proportional to the energy that we're expending for that paddle to come down to 90 degrees. You could actually do the math for this to go all the way to 180 degrees, but it'll be the same efficiency, so I'm just stopping at 90 degrees to simplify the math. So the area of water that we're pushing, or the volume or the mass, it's going to be 1/4 pi r squared. Pi r squared is the area of a circle. We're displacing 1/4 of that circle of water. If we have a diameter of 2, that'll be a radius of 1. So 1/4 of pi would just be pi over 4. That's the amount of mass or the amount of energy that we're displacing on this water right here. Notice that this is one of the things I had to figure out too. This pi over 4, this is not in radians, because pi over 4 means that it's at 45 degrees. So that pi over 4 actually means you take your radius, which is 1 for a unit circle, you multiply that times pi over 4, and then that is the length around the circumference that you travel. But in this case, the pi over 4 does not mean radians. It actually means 1/4 of the circle, or I should say 1/4 of the whole circle, and not 45 degrees. Because 1/4 of the whole circle is actually 90 degrees. So I'm not sure, I said this might be more related to diameters because pi times diameter gives you the circumference. But again, this is just one of the difficult things I had to figure out, that this pi over 4 is actually not in radians. That is actually the area of the circle, or that's actually 1/4 of the circle that we're pushing, or that's, how should I say that? That's 1/4 of the area of the circle that contains the water mass that we're pushing, and that's equivalent to our energy. And if you look at pi over 4 radians, that is actually 1/8 of a whole circle. So again, this is going to be a long video, or it's going to be a longer video while I sort through all of this, but all these little complications just kind of kept popping up and surprising me. The graph I'm going to show is just going to represent efficiency and not the amount of energy or the amount of mass of water. Oh, almost forgot. One thing I want to show on this, the amount of mass of here, because notice here we're just pushing 1/4 of the circle as the mass of water. We could actually compare this to the linear system that we have from the track. If we have an amphibious vehicle with tracks on it, they're going to push a mass of 1. It's going to be 1 by 1 as that track moves backwards in the x direction. So I just wanted to show that to show that there's different ways to think about the energy and the mass of water that we're pushing. And next page. Here I'm just going to graph out the sine wave across the bottom on the x-axis here. It says pi over 4 or pi over 2. That's the same as 45 degrees, 90 degrees. Notice this x-axis is only going to be the distance. It's distance only by the tip of the paddle wheel, meaning the tip that this paddle wheel covers from here down to here, from 0 down to 90 degrees. That distance is going to be pi over 2 radians. So actually I found out if I wanted to, I actually don't have to use radians. I could actually use degrees right here, or I could use actually any number along the bottom, because all I'm doing is comparing the efficiency of a paddle wheel with the water at axle level, the water at 45 degrees, and then a vertical bucket paddle wheel, which is right here. Where we have maximum efficiency. Oh, I forgot, the water level actually is right here on a vertical bucket paddle wheel. If you're going to use this 4-bar linkage system right here, because this part right here will sink down into the water and push back and then come back up, and it just spins in circles. Okay, so again, this x-axis is only the distance covered by the tip of the paddle wheel. It's not actually the distance that we're pushing water. That was the whole point of this thing that I was talking about. Because if it was the total distance of a mass of water, then we're actually looking at the amount of energy, but we're actually not going to get energy on this. The y-axis is going to be the force in the x direction, meaning when that paddle wheel is at 0 degrees, all of our force is in the y direction pushing down if that water level is at axle level. And then when you get up to say pi over 4 or 45 degrees, the sine, you can take the sine of that value, it'll give you another number, and what that sine of that angle will equal is going to, that will equal the amount of force being pushed in the x direction. So even though force times distance equals energy, this x-axis is only the distance only by the tip of the paddle wheel and not the actual distance that we're pushing a mass of water. It took me quite a while to figure that out. And this is where I was saying I got the answer, and I think I got the right answer, but I really didn't know what the answer represented. Here's a part that was confusing also. When you're looking at a linear system with a tracked vehicle, this whole mass of water gets pushed 1 unit over, so that's easy to calculate. If you have 1 kilogram of water and you push it 1 meter or whatever, now you have your energy. But when you're turning about an axis right here, you could have little molecules of water right up here by the axle, and they could just be pushed 1/1000th or 1/1,000,000th of the length of the radius right here. But then the water molecules way out here at the end of the radius of the circle, they're going to be pushed pi over 2 radians, which is like 1.6 or something. So if your radius is 1 meter, then the water molecules right here on the very tip are going to be pushed 1.6 meters as they get pushed 90 degrees. But the little water molecules up here right by the axle, they're just going to be pushed a couple of millimeters or less. So like 1/1000th of the distance of your radius or less. So that's why calculating the actual distance that this water is being pushed to get the energy, that just doesn't work out for this graph right here. So that's why this x-axis is simply the distance that the radius covers, or the tip of the paddle wheel right at the edge of the circumference. And it's not actually the distance that the water molecules are being pushed. So even though force times distance equals energy, it doesn't seem to do that in this situation. And again, this took me a while to figure out. Okay, now right here, this box, see how it makes a rectangle? This is 100% efficient, and this would be a vertical bucket paddle wheel. Because a vertical bucket paddle wheel, no matter at what angle this comes down, that paddle stays vertical, so you're pushing all your energy in the x direction. There's no energy being pushed down in the y direction. So you could take this right here at say I don't know, 2 degrees or at 5 degrees or wherever you want, you're going to take the sine of 90. So it's going to be the sine of 90 across the entire top here, because with a vertical bucket paddle wheel, this paddle is always at 90 degrees. So you're going to end up with a complete rectangle. So if you want to calculate your efficiency, or let's just say that this is 100% efficient, you take the force in the x direction, which will be 1, take pi over 2, right there, radians, and so you take 1 times pi over 2, you get pi over 2. And that is an ideal situation where you have 100% efficiency with a vertical bucket paddle wheel. And then what we do is compare a normal paddle wheel here with water at axle level. And that's where I said you could actually just take an average of sine of 5, sine of 10, sine of 15, sine of 20, and then average all those sine values together to find out what your average energy is, or what the average force is in the x direction. But a sine wave looks like this from 0 to pi over 2. And you could break your x-axis up into a bunch of little slivers if you want. Each little sliver could be 1 degree. So let's say we have 90 slivers from 0 to 90 degrees, or from 0 to pi over 2. So the first 1/90th of that segment, or the first 1/90th of that little column, will be 1 degree. Then the second 90th will be 2 degrees. And then you'll just have a whole bunch of little columns right here to get your area under the curve. And I'll show how to use the area under the curve to get our efficiency. You could just compare your areas. For a perfectly efficient vertical bucket paddle wheel, we'll have base times height, pi over 2 times 1 equals pi over 2. If we take the area underneath this sine wave right here, we'll actually get 1, and I'll show how to do that. So you can take 1 divided by pi over 2, and you'll get 2 over pi, which is about 64%. So that means the area under this curve is about 64% of the whole rectangle. And then that means all this wasted space right here encompasses 36% of this rectangle and represents 36% wasted energy by pushing down in the y direction, or force in the y direction. When we raise the paddle wheel up so that the paddles contact the water at 45 degrees, then we only want the efficiency from pi over 4 to pi over 2. Because here's pi over 4 when the paddle contacts the water, and here's pi over 2 right here. You could double this length if you want to, but you'll get the same ratios. So I'm just looking at the, say, the front of the paddle wheel right here. I guess I should show these arrows coming down here. The paddle wheel is spinning clockwise as we look down on it. So right here, just the sine of theta equals the fraction force in the x direction, which also equals the efficiency. Notice right here we have very little wasted space up here because we're looking at about 90% efficiency. So when you look at this square right here, 90% of the area lays underneath the area under the curve. And then there's another 10% right up here on top that's wasted, and that's your force in the y direction from the paddle pushing down. I'll show how I got those numbers. Next page. Real quick, the confusing part here, I remember when I said that this paddle wheel is pushing down, you're pushing 1/4 of the circle. That's pi over 4, and that pi right here is related to the diameter, not radians. And if we look at this right here, if you take your force times distance equals energy, take 1 times pi over 2, because you have pi over 2 on your x axis, 1 right here, you're going to get pi over 2 as the energy pushing in the x direction. Or you could say that's the force pushing in the x direction. But just notice that that pi over 2 does not equal pi over 4 from the vertical bucket paddle wheel, because we're looking at 2 separate graphs here, 2 separate systems. Importantly, the pi over 2 is the distance traveled only by the tip of the paddle wheel. So I'm showing this to show again that this does not represent an actual energy, even though we're multiplying force times distance to get the area under the curve. That's not actually the energy or the amount of mass of water that we're pushing. I could actually get the same numbers and the same ratios if I wanted to use degrees down here on the x-axis instead of radians. And this is where I was wrong before, because I thought you had to have a length down here, the length of the circumference measured in radians, or I guess you'd say radiuses of the circle. But since all I'm doing is looking at a ratio of the area under the curve of the sine wave compared to the area of the whole rectangle, I could pretty much have any numbers along the bottom here. And that's, well, let's see, I just said here pi over 2 is the distance traveled only by the tip of the paddle wheel, and it's in radians. It does not equal pi over 4. That comes from the diameter of the whole circle, and that which is 1/4 of the circle. That's proportional to the mass of water we're pushing, which is proportional to the total energy that we're expending. And the graphs are not total energy, they're really just graphing the efficiency. And again, this took me a very long time to figure out. I don't know, a couple days probably thinking about it. Okay, next page. And right here I just said base times height equals your area. Your base is from 0 to pi over 2. The height is 1. Pi over 2 times 1 equals pi over 2. This will be our baseline of a 100% efficient system. So we want the area of that rectangle, 100% efficiency. To get the area under the curve for the sine wave right here, you just take the integral of sine theta d theta evaluated from 0 to pi over 2 right there. Integral of sine theta equals negative cos theta. Go ahead and plug in your numbers. We have negative cos pi over 2 minus negative cos 0, and that'll equal the area. Cos pi over 2 is 0, minus negative is positive. We just end up with cos 0, which equals 1. That is the area under the curve of the sine wave right here, just 1. And next page. To get our efficiency, we can just compare the areas under the curves and the lines. The area under the paddle wheel divided by the area under the ideal rectangle equals efficiency. 1 is the area under the curve for the paddle wheel. Pi over 2 is the area of the rectangle for a perfectly efficient system of a vertical bucket paddle wheel. 1 divided by pi over 2 is just 2 over pi, so about 64%. So about 64% of the energy of a paddle wheel is pushing backwards in the x direction to provide forward motion. 36% of that energy is wasted energy, either pushing down in the front of the paddle wheel or pushing up in the back of the paddle wheel. And again, I only evaluated the paddle wheel from 0 to 90 degrees. When we flip our unit circle upside down here, I didn't evaluate the back part where the paddle is pushing up, but it'll give the same percentages. The other way to compare efficiencies, base times height equals your area. We know the area equals 1 is the area under the curve. Area divided by base equals height. The base is pi over 2. And again, we end up with 1 divided by pi over 2, which is 2 over pi, 64%. The same answer that we had up here. So I thought that was kind of interesting. 2 different ways to use the area under the curve to get the efficiency of a paddle wheel. Next page. Actually, before I go to the next page, I want to say the same thing that I say in all my videos where I cover the area under the curve. And the reason I want to say this is because I haven't seen it taught this way, and it was just something I figured out. We have this entire mound right here. Let's say it's like a mound of Play-Doh or something in a narrow aquarium. We want to get the average height here. We have it's tall right here and it's short down at the bottom. We want the average height, so that means what we can do is actually squish this down to form just a rectangle. And now that we have our rectangle, we can take the base times the height of the rectangle to get the area. We know the area of our Play-Doh mound right here is 1. We know the base is pi over 2. So base times height equals area. That means area over base equals your height. And that gives us our 64%, which means if you were to squish this mound of Play-Doh or modeling clay or whatever down, then this line right here, you'd have a horizontal line right at the 64% mark compared to the 1 right there on the y-axis. Okay, next page. Now for a different system, because we're looking at the paddle wheel that's raised up and the paddles are only contacting the water at 45 degrees. So the paddle's in the water from 45 to 90. I'm just looking at the front or the fore section of the paddle wheel, not the aft section. So that is the area between pi over 4 to pi over 2. So we take pi over 2 minus pi over 4 to get base times 1 for the height. Base times height equals area. Pi over 2 minus pi over 4. And we can pull pi out of this equation right here to make this simpler. We end up with 1/2 minus 1/4, quantity times pi. 1/2 is the same thing as 2/4, so we get 2/4 minus 1/4, which is 1/4 times pi, or pi over 4. This is 100% efficiency. The area under this rectangle or this square right here is pi over 4. Now let's look at the area underneath the curve here of the sine wave between pi over 2 and pi over 4. We take sine theta d theta, evaluate it from pi over 4 to pi over 2 to get the area, and that equals negative cos theta from pi over 4 to pi over 2. And next page. Cos of pi over 2 is 0, so we got 0 minus negative cos of pi over 4. That'll be root 2 over 2 is our answer. That is the area underneath the sine wave is root 2 over 2 between pi over 4 and pi over 2. Let's compare the two areas. Let's take the area under the curve of the sine wave divided by the area of our rectangle from a perfect system. Root 2 over 2 divided by pi over 4 gives you root 2 over 2 times 4 over pi, and that equals 2 square roots of 2 divided by pi. That comes out to be about a 90% efficiency. That means that 90% of this rectangle right here, 90% of this area is under the curve of the sine wave. There's another 10% of the area up here that's wasted. And that is the amount of energy pushing down in the y direction. Again, not considering the energy of frictional losses or heat losses from an engine or something. We can also use the equation base times height equals area. Area over base equals height. The area is 2 square roots of 2 divided by pi. The base equals pi over 4, and that's between pi over 2 to pi over 4. And we get the same answer, 2 square roots of 2 divided by pi, which again is 90% efficiency by raising the paddle wheel up out of the water so that the paddles contact the water at about 45 degrees. Or I guess I should say at 45 degrees.